Beyond the orbit of Mars, the solar system stops feeling familiar. The sun shrinks into a distant glow, light weakens, and time itself seems to slow down. Jupiter rises not as a planet, but as a gravity giant surrounded by moons that hide oceans beneath ice and volcanoes that erupt endlessly. Saturn follows with rings that are not gentle or fragile, but violent streams of rock and ice racing through space. Farther out, Uranus spins on its side as if something struck it long ago, while Neptune unleashes winds faster than sound in eternal darkness. And beyond even that lie, frozen worlds so distant that sunlight barely exists. This is not the calm edge of our solar system, but a realm of extreme physics, unsolved mysteries, and places humanity was never meant to reach. Get ready, we begin. Before the Voyager spacecraft arrived in the Neptunian system, this distant planet was the least understood of all the worlds in our solar system. You cannot see Neptune with your naked eye. Even when viewed through the most powerful telescopes on Earth, it appeared as nothing more than a blurry ball of blue and green colours. Neptune is the fourth largest planet by volume and the third largest by mass. From our distant viewpoint on Earth, we knew almost nothing about what made up its atmosphere or how the planet was structured inside. We had only faintly observed two moons orbiting around it, Triton and Nereid. This was a planet that had stayed firmly in the darkness, a distant world that had held onto its secrets tightly for more than 140 years. Even the story of how Neptune was discovered happened in darkness. Neptune was the last planet in our solar system to be found. It holds a unique distinction. It is the only planet whose existence we predicted using mathematics before any human ever saw it through a telescope. For hundreds of years, people looked at Neptune in the night sky without knowing what they were actually seeing. Almost certainly, the famous scientist Galileo was the first person to point a telescope directly at Neptune. This happened during a series of observations he made at the end of 1612 and the beginning of 1613. The data he recorded with his newly invented telescope led him to believe this object was a fixed star in the night sky, not a moving planet. Over the next 200 years, many astronomers must have pointed their telescopes at this dim star without realizing the importance of its bluish light. But the first hint of Neptune's true nature would not appear in a telescope eyepiece. Instead, it came from a set of astronomical tables. In 1821, a French astronomer named Alexis Bouvard published a book called Table Astronomique. This book contained tables that predicted the orbits of the three outer planets known at that time: Jupiter, Saturn, and Uranus. Bouvard based his predictions on Newton's laws of motion and universal gravitation. Over the next few years, scientists tested Bouvard's theoretical work against the actual movements they observed in the night sky. His careful calculations were proven correct when observations of Jupiter and Saturn's movements matched precisely with his mathematical predictions. However, Uranus refused to behave as expected. The movement of what was then the farthest known planet deviated substantially from Bouvard's predicted path. This unexpected result led Bouvard to make a wild suggestion. He proposed that either Newton's laws were wrong, or perhaps there was an undiscovered planet lurking in the darkness. This unseen planet could be pulling on Uranus through gravitational interaction, distorting its path through space. This suggestion sparked a flurry of activity. Astronomers rushed to find the hidden planet, which would be the ultimate prize for any stargazer. Bitter race kicked off between the British and French to predict the planet's location. On the British side of the English Channel, a Cornish astronomer and mathematician named John Couch Adams became obsessed with Bouvard's idea. Adams was convinced he could use nothing more than pen and paper to determine the size, position, and orbit of this hidden world. By September 1845, Adams had at least partially completed his calculations. But unknown to him, almost at the same time, a French mathematician named Urbain Le Verrier in Paris was completing his own complex calculations of Uranus's path and the mysterious eighth planet. By the summer of 1846, Le Verrier had finished his work. On August 31st, he announced to the French Academy that he had calculated a predicted location for the missing planet. He revealed his work just 2 days before Adams secretly sent his own prediction in a letter to the Royal Greenwich Observatory for verification. In what must be one of the most close-run races in scientific history, Le Verrier engaged the Berlin Observatory in the search for his predicted planet at 12:15 a.m. on the night of September 24, 1846. Johann Galle, with help from his assistant Heinrich d'Arrest, looked through his refracting telescope. At that moment, he became the first person to knowingly look at the eighth and furthest planet in the solar system. A planet that had taken decades to locate was found in less than an hour. Even more remarkably, it was found within 1 degree of the position Le Verrier had calculated using pure mathematics. Even today, the exact credit for discovering Neptune is still disputed. But in the winner-takes-all world of astronomical discovery, history records Le Verrier as the discoverer of Neptune, the man who discovered a planet with the point of his pen. It took another 143 years before we would visit Le Verrier's planet. When we finally did, we witnessed a dynamic, violent, and volatile world. As Voyager drew closer to Neptune, it began returning a precious set of images. These images remain to this day our only close-range record of this planetary system. At first, Voyager flew past Nereid, the third largest of Neptune's moons. The spacecraft captured our only image of this distant world as it travelled on its massively eccentric orbit around the planet. But it was the images of Neptune itself that became increasingly amazing and unexpected. Painted across the surface of the planet, Voyager revealed banks of methane clouds. These clouds were being whipped around by high-altitude winds at speeds of over 2,000 kilometers per hour. These winds were at least 5 times stronger than the most powerful winds ever measured on Earth. They were the highest wind speeds we had witnessed anywhere in the solar system. The violent winds weren't the only surprise. Through Voyager's cameras, we could see great hurricane-like storms moving across Neptune's surface. The largest storm was an Earth-sized system similar to the Great Red Spot on Jupiter. Scientists named it the Great Dark Spot. Voyager took multiple images of this vast storm system as it sped past the planet, skimming the cloud tops of the northern pole from a distance of just 4,400 kilometers. This closest approach occurred on August 25, 1989. No one had expected such massive storms to be brewing so far from the Sun, but just 5 years later, when the Hubble Space Telescope was up and running, we looked back toward Neptune. Scientists found that the Great Dark Spot had disappeared. Unlike the giant storms on Jupiter, which we've watched playing out for centuries, it seems that the weather on Neptune is far more temporary. The largest storm events come and go within just a few years. The intense weather systems that we witnessed on Neptune remain a tantalizing puzzle for scientists. On average, Neptune is 50% farther from the Sun than Uranus. It receives just 40% of the sunlight that hits its sister world. The surface temperatures of both planets are equally intensely cold. In fact, the temperature of Neptune's outer atmosphere is one of the coldest places in the solar system. Temperatures at its cloud tops measure around -220 degrees Celsius. Orbiting this far out in the frozen reaches of the solar system explains the blandness of Uranus's weather. But why would Neptune, even farther from the Sun, be so active? The answer, we think, lies in a mysterious and powerful source of heat that we have detected coming from deep within the planet. All of the planets, including Uranus and Neptune, have some leftover heat locked deep inside them. Much of this is thermal energy that remains from the endless collisions during their creation. Additional heat comes from the radioactive decay of certain elements in the core. However, this far out, Uranus has rapidly lost this heat. Today, it radiates just 1.1 times the energy it receives from the Sun. The heat radiating from its core is too little to drive any kind of dynamic weather system through its atmosphere. Neptune, it seems, has a far warmer heart. Voyager was able to reveal that the most distant planet radiates 2.61 times as much energy as it receives from the Sun. These unexpectedly high temperatures help explain the violent storms we see in its atmosphere. As the heat makes its way from the core of the planet out into space, it churns up the entire atmosphere. This creates winds of extreme strength. Once they start, there is little to stop them. Neptune, like Uranus, is what scientists call an ice giant. It's a planet composed of a rocky core and a mantle made up of water, ammonia, and methane ices. All of this is surrounded by a cold gaseous atmosphere. With no solid surface on the planet, there are no mountains or continents to break up the flow of the atmospheric gases. This means the winds can whip around the planet, picking up speed until they are quite literally supersonic, faster than the speed of sound. All of this helps give us a reason for Neptune's extreme weather, but not a complete explanation. Voyager 2 was unable to reveal why Neptune and Uranus are so different. We still don't know what it is about Neptune's formation that left it with far more residual heat, making it the far more active of the two planets. Neptune's active atmosphere was not the only surprise Voyager returned to us. The pictures from its two-camera system showed vibrant and vivid detail. The images also revealed that the solar system is home to not one, but two blue planets. Neptune is a bright blue world, but with no liquid water on its surface, we know that the origin of this color cannot be the same as here on Earth. This deep cobalt color must be produced by something else in Neptune's atmosphere. Voyager provided the answer using its onboard spectrometer. This instrument was able to measure for the first time the composition of Neptune's atmosphere. It found the atmosphere to be comprised of 80% hydrogen, 18.5% helium, and 1.5% methane. Methane was by far the smallest component, yet this is the key to understanding Neptune's blue hue. The light of the Sun contains all the colors of the rainbow. But as it hits the surface of a planet, it interacts in different ways depending on the molecules it encounters. In the case of Earth, the water that covers our planet absorbs all of the red light in sunlight. So as the Sun strikes the surface, only the blue light is reflected back. It's the same with all the plants on our planet. The chlorophyll in plants absorbs the blue and red light, so only green light is reflected back. On Neptune, there is no water to turn the planet blue. Instead, it's the methane that absorbs the red light of the dim and distant Sun. This reflected blue light then bounces back out into the darkness of space. But things aren't quite as simple as they first appear. Uranus is also a blue world, but just a bit paler and greener in shade compared with its more distant sibling. And yet Uranus also has methane in its atmosphere. In fact, it has slightly more methane than Neptune. So Uranus, not Neptune, should be the darker shade of blue. Why is this not the case? Well, quite wonderfully, we still don't know the answer. Voyager looked for other substances in Neptune's atmosphere that could account for the deeper blue color, but it found nothing that could explain the difference. So for now, the many differences between these two worlds remain a mystery. After over 12 years of traveling, Voyager 2 completed its grand tour of the solar system. This tiny explorer had set out from Earth and travelled across 7 billion kilometres of space. It made a single extraordinary journey to explore all of the outer worlds of the solar system: Jupiter, Saturn, Uranus, and Neptune. But before it began its long, lonely journey into the darkness of interstellar space, there was one more brief encounter left on its schedule. While in the Neptunian system, Voyager had made endless discoveries. These included the detection of a faint ring system and the confirmation of 6 new moons in orbit around Neptune. In those final hours of close contact, as Voyager flew across the north pole of the planet, mission scientists back at the Jet Propulsion Laboratory had instructed the spacecraft to make one last bold maneuver. This was a close flyby of Neptune's giant moon, Triton. Just 5 hours after nearly touching the cloud tops of Neptune, Voyager travelled within 40,000 kilometres of the Neptunian moon. It returned the first pictures of this strange and distant world. The British astronomer William Lassell first spotted Triton on October 10, 1846. This was just 17 days after the discovery of Neptune itself. As astronomers rushed to observe the newly identified planet, it was Lassell with his homemade telescope who noticed the satellite first. Although Triton was not officially named until many years later, it would remain the only known satellite of Neptune for over 100 years. It wasn't until 1949 that Gerard Kuiper discovered Nereid, Neptune's second moon. As Voyager returned the first images of Triton, it immediately became clear that, just like Neptune, Triton was far more active than we had ever imagined. Here in the furthest reaches of space, the 7th largest moon in the solar system was far from a frozen, inactive rock. It was a geologically active world with features unlike anything we had imagined. Voyager was only able to image about 40% of Triton's surface because most of the northern hemisphere was in darkness. But what it revealed was fascinating. Triton has a sparsely cratered exterior with a strange network of ridges and valleys covering its entire surface. In the western hemisphere, there's a region nicknamed the Cantaloupe Terrain because of its striking similarity to the skin of a melon. All of this evidence pointed to the fact that the surface of Triton is young, not battered and ancient like that of our moon. Even though Voyager's instruments recorded it as one of the coldest places in the solar system at -235 degrees Celsius, the surface seemed to be resurfacing through active volcanism occurring across the moon. But this was not volcanism as we understand it here on Earth. There is no molten rock beneath the surface of Triton. This is an ice world with a surface covered in a frozen mixture of nitrogen, water ice, and carbon dioxide. Any volcano that exists here would be what scientists call a cryovolcano. These volcanoes erupt water, ammonia, and methane from below the surface. This cryomagma immediately solidifies in the extreme low temperatures of the surface. As Voyager looked closer at the surface of Triton, it captured a series of images of the southern polar region. These images appeared to provide evidence of such geological activity. Lurking among the flat volcanic plains and rift valleys was a set of distinct features that immediately caught scientists' attention. Scattered across the surface were what appeared to be at least 50 dark plumes. Voyager was travelling so fast and was so far away from the moon that it was unable to get close-up images of these intriguing plumes. But we are certain that they are evidence of ice geysers. The dark streaks of dust deposited on the surface are left behind by the eruption of these geysers. According to planetary scientist Noah Hammond, it was a big surprise to see active geysers on Triton, shooting material 8 kilometers into the air. Scientists think these geysers might be forming as a result of nitrogen ice being vaporized by the sun. Both of the geysers that Voyager 2 observed are concentrated on the warmest part of Triton, where the sunlight strikes the hardest. As the sunlight pierces through the nitrogen ice, it starts to turn that nitrogen ice back into a gas. This gas builds up and builds up until it has enough energy to break through the ice. It then lifts dust all the way up into the atmosphere. Further analysis of the images suggested that at least 4 of these geysers were active at the time of Voyager's flyby. They were belching clouds of ice and dust 8 kilometers up into the thin Neptunian atmosphere before falling back down to the surface over 100 kilometers downwind. Perhaps even more astonishingly, we have been able to formulate a hypothesis for the mechanism that lies beneath these geysers. The key to understanding why this wondrous geological activity occurs in the most unlikely of places seems to involve their location on the surface of Triton. From the imaging data that Voyager 2 returned, it seems the geysers tend to erupt on the most sunlit part of Triton's surface. From a distance of 4.5 billion kilometers, the sun's rays are faint. The amount of thermal energy landing on the surface is low, but combined with the specific chemistry on Triton's surface, the effect of the sun can still be dramatic. What seems to be happening is that sunlight falling on the thin layer of nitrogen ice covering Triton penetrates the surface. It then heats up a layer of darker methane particles about 1 meter below the surface. The methane acts as a subsurface greenhouse gas, trapping the heat below the surface. It radiates that heat back up through the frozen nitrogen. Even though this mechanism creates a temperature difference of just 4 degrees Celsius between the surface temperature and the warmer interior, this small difference is enough. It melts the frozen nitrogen and creates pockets of gas sitting beneath the nitrogen ice. This gas is kept under pressure, building up until it ultimately punches through the nitrogen ice. This creates the geysers of Triton, carrying the dark ice particles up to 8 kilometers into the sky. Although the faint light of the sun is just strong enough to power Triton's geysers, it's simply too weak to have driven the other geological processes. These processes created the network of valleys, crevasses we see all across the surface. It seems that something in Triton's past must have heated the moon enough to drastically alter its terrain. A potential clue to the source of that ancient heat can be found in the oddity of Triton's orbit. Unlike every other large moon in the solar system, Triton orbits in the opposite direction to the spin of its planet. Triton travels around Neptune in a tidally locked orbit with the same side facing inward at all times. But it orbits in a clockwise direction while Neptune spins on its axis anti-clockwise every 16.11 hours. Such disagreement between planet and satellite suggests that it is very unlikely that Triton and Neptune formed at the same time. A planet and moon system fashioned from an identical collapsing cloud of gas and dust at the same moment would tend to spin and orbit in the same direction. This matches the spin of the initial dust cloud, just like the overwhelming majority of moons we see in the solar system today. So the most likely explanation is that Triton joined Neptune much later. It was a visitor to the Neptunian system that, unlike Voyager, never left. Like Uranus, we don't know for certain the deep history of Triton, but all the evidence from its orbit and surface features points to the possibility that long ago, Triton was not a moon at all. To understand where Triton might have come from, we need to look beyond the Neptunian system and peer further out into the darkness. It was only relatively recently that we confirmed the existence of a region of the solar system now known as the Kuiper Belt. This is a disk of millions of objects that stretches out from the orbit of Neptune to at least 50 astronomical units from the Sun. The Kuiper Belt is similar to the asteroid belt in structure, but far larger in scale. We had long suspected that such a region might exist, but it wasn't until 1992 that we were able to put together a body of proof. That year, astronomers discovered an icy object known as Albion. This discovery was a turning point in our knowledge about our solar system. According to Alan Stern of the New Horizons mission, the Kuiper Belt was revolutionary. It's so far from the Sun that temperatures out there are almost absolute zero. Everything is so well preserved. It's like an archaeological dig into the early history of our solar system. It's a scientific wonderland. Albion was the first trans-Neptunian object to be identified since the discovery of Pluto and its moon Charon. This finding launched a flurry of further discoveries. Today, we've identified around 2,400 objects in the Kuiper Belt region. We think there are at least 100,000 objects bigger than 100 kilometers wide in the Kuiper Belt. Just like the asteroid belt, this dispersed region of debris is composed of remnants from our solar system's formation. But whereas the asteroid belt is a disk of rocky fragments, we think the Kuiper Belt is made up of icy objects. Methane, water, and ammonia are the major ingredients. It's that list of ingredients that leads us back to Triton and its strange history. We now believe that perhaps long ago, Triton grew up in the Kuiper Belt among millions of other frozen lumps of water, ammonia, and methane circling the Sun, before something, such as a collision, disturbed its orbit and flung it inwards. Plucked from the Kuiper Belt, Triton would be captured by the gravitational pull of Neptune and forever trapped in its strange orbit around the blue planet. Today, Triton orbits in a nice regular circle around Neptune, a bit like the way our moon orbits around Earth. But to begin with, this newly captured satellite would almost certainly have been in a chaotic orbit. Glancing past the planet, it would have started along a wide elliptical path around Neptune, bringing it from far out to close in on every revolution. This would have meant that as Triton orbited Neptune, the gravitational pull would be constantly changing. This would stretch and squash the moon, just as Jupiter does to its moon Io today. The result is that the friction of these tidal forces would have heated up the interior of Triton. This would have created far more activity than the erupting geysers we see today. Through this process of tidal heating, the ancient interior of ice would have become molten and volatile. It would explode up through cracks and faults in the moon's crust, creating the ragged surface we see today. Over time, as the orbit adjusted into a more regular circular path, the friction reduced. The heating diminished. What we're left with is an icy, frozen moon circling the wrong way around its planet. The subtle scars of its early life are written across its surface. All that remains today of that dramatic, violent past are the geysers, powered by the faint light of the sun, painting dark streaks across the now quiet surface. As Voyager 2 sped away from Triton and Neptune at over 60,000 kilometers per hour, the planetary exploration phase of this extraordinary mission finally came to an end. Its exploration would continue beyond even the furthest reaches of our solar system and extend into the unknown depths of interstellar space. But its time as a planetary explorer was over. A tiny spacecraft built with 1,000 human hands had shone a light into the darkness. It revealed the secrets of worlds that had been hidden in the night for over 4 billion years. As yet, we have not returned. While Neptune and Uranus have fallen back into the distance, viewed only through the lenses of our most powerful telescopes, another even more distant world was waiting for our first arrival. Mars appears red to our eyes and has been associated with war and blood since ancient times. Through a small telescope, it's the most Earth-like of planets. We can see polar ice caps and what look like deserts. A world we could imagine visiting, perhaps even settling. In the 19th century, astronomers convinced themselves they saw plains and mountain ranges and even canals. Some thought these canals delivered meltwater from high latitudes to dry equatorial cities. Many believed the Martians were a peaceful civilization far in advance of our own. Others, like H.G. Wells in his 1897 novel The War of the Worlds, saw a threat. He wrote about minds that are to our minds as ours are to those of the beasts that perish. Intellects vast and cool and unsympathetic that regarded Earth with envious eyes. The nature of Mars remained a mystery until well into the 20th century. The planet is small and far away, making it difficult to view with ground-based telescopes. Even the Hubble Space Telescope, high above the distorting effects of Earth's atmosphere, produces images that would not have prevented Wells from publishing his novel. Everything changed on July 15, 1965, when NASA's Mariner 4 spacecraft made the first flyby of Mars. The photographs revealed an arid surface that looked more like our desiccated moon than our blue planet. Overnight, we discovered for certain that Earth is the only planet in the solar system capable of supporting complex life. In November 1965, the Bulletin of the Atomic Scientists published an article about Mariner 4's findings. The message was bleak. The shock came not only from the denial of a terrestrial image of Mars, but from the revelation that there is no second chance, at least not in the solar system. President Lyndon B. Johnson reportedly commented, "It may be, it may just be, that life as we know it with its humanity is more unique than many have thought." The hesitation in those first few words is revealing. Here was Mars as a symbol of our cosmic isolation. Deep in the subconscious, the 1960s power brokers all the way up to the president suddenly understood that Earth is far more fragile and precious than their Cold War actions might suggest. But our understanding was incomplete. Mariner 4 took only 22 photographs with a resolution of over a kilometre. Carl Sagan and his co-authors wrote a paper suggesting that all was not lost. Using thousands of photographs of similar resolution taken by weather satellites orbiting Earth, they found only a single feature that clearly indicated the presence of civilization: Interstate Highway 40 in Tennessee. They concluded that Mariner 4 would not have detected human civilization if it had flown by Earth. They wrote, "We do not expect intelligent life on Mars, but if there were intelligent life on Mars comparable to that of Earth, a photographic system considerably more sophisticated than Mariner 4 would be required to detect it." The Mariner 9 mission in November 1971 became the first spacecraft to orbit another planet. It achieved a photographic resolution of 100 meters per pixel. No sign of intelligent life, past or present, was detected. The twin Viking landers in 1976 failed to detect even microbial life, although the results of their biology experiments are not considered totally clear. In twice hindsight, the fact that Mars is not teeming with life today is not so surprising. Mars orbits 50 million miles farther from the Sun than Earth. It receives less than half the solar energy. It's a small world with a thin atmosphere that provides little insulation or greenhouse warming. NASA's Curiosity rover in Gale Crater has measured midday temperatures above 20 degrees Celsius, but in the early hours of the morning, it has experienced minus 120 degrees. As Alfred Russel Wallace wrote in 1907, any attempt to transport water across the Martian surface today would be the work of madmen rather than intelligent beings. There are no canals, no cities, and no envious eyes. The planet is a frozen, hyper-arid desert, too far from the Sun to support complex life. Yet it hasn't always been this way. Observations from our fleet of orbiting spacecraft and landers have revealed a complex and varied past. Once upon a time, the red planet was glistening blue. Streams ran down hillsides. Rivers wound their way through valleys carved by a water cycle. From land to sky, and down again, from mountains and highlands to the sea. This presents a great challenge for planetary scientists. Put simply, nobody would have been surprised if Mars had always been an inert rock. It's a small planet far from its star. But the geological evidence is clear. The surface tells a different story. Mars remains an enigma. A map of Mars can be read like a history book. Unlike Earth, where constant weathering, tectonic activity, and volcanism have erased the deep geological past, Mars has been relatively quiet for most of its life. The scars of collisions from the first turbulent billion years after the formation of the solar system can still be seen from orbit. Ancient catastrophes are documented below a thin film of dust. NASA's Mars Global Surveyor spacecraft spent 4.5 years mapping Mars in the late 1990s. It provided detailed maps with colours corresponding to differences in altitude. Just as on Earth, there is significant variation in height, but the geological features on our smaller sister world are much bigger and bolder. The highest points on Mars are found on the Tharsis Rise, a great volcanic plateau. It's home to the largest volcano in the solar system, Olympus Mons. At over twice the height of Mount Everest, Olympus Mons towers 25 kilometers above the lowlands. Its base would fit inside France. Cutting a deep scar across Tharsis is Valles Marineris, named after the Mariner 9 spacecraft that discovered it. This canyon dwarfs anything on Earth. The Grand Canyon would fit into one of its side channels. The lowest points on Mars are found in the Hellas Impact Basin, the largest clearly visible impact crater in the solar system. From the highest points on the crater rim to the floor, Hellas is over 9 kilometers deep. It could contain Mount Everest. These are extreme altitude differences for a small world, over 30 kilometers from the summit of Olympus Mons to the floor of Hellas. On much larger Earth, for comparison, there is only 20 kilometers difference between the summit of Everest and the Challenger Deep in the Mariana Trench. The most striking and ancient elevation difference on Mars is between the northern and southern hemispheres, known as the global dichotomy. Mars is an asymmetric world. The northern hemisphere is on average 5.5 kilometers lower in altitude than the southern. There is no agreement on how the dichotomy formed, other than that it was early in the planet's history. The oldest terrain on Mars is found in the Noachis Terra region of the southern highlands. It's characterized by heavy cratering, reminiscent of the far side of the Moon. Even small craters in the Noachian highlands are heavily eroded, which suggests the regular presence of liquid water. There are dry river valleys and deltas, and evidence of water pooling in the craters and overflowing their walls. This formed interconnected networks of lakes. This is how we know Mars was once a warmer and wetter world. The persistence of surface features over many billions of years has led to the historical periods of Mars being named after distinctive terrains. The Noachian period was the earliest and wettest. It coincided with the origin of life on Earth around 4 billion years ago. Conditions on both worlds appear to have been very similar then. The Martian atmosphere may have been thicker than Earth's and dominated by carbon dioxide. But significant questions remain about how such an atmosphere could have warmed Mars enough to deliver warm, wet conditions. And how was that atmosphere lost? The Noachian period ended as Mars became increasingly cold and dry around 3.5 billion years ago, just as life was gaining a foothold on Earth. The Hesperian period followed, the time of catastrophic floods. It ran from the end of the Noachian to around 3 billion years ago. Mars then entered its current frozen dry phase, punctuated by occasional volcanic activity and large-scale movement of ice, but with very little evidence of flowing water. The long 3 billion year freeze from the end of the Hesperian to the present day is known as the Amazonian. This is a summary of what we know about Mars. The facts pose a significant challenge. Given a warm, wet, and seemingly stable world early in its history, what triggered the loss of atmosphere and descent into modern-day dryness? What happened to the water on Mars? Was it lost to space, or does it still exist today as surface ice or in subsurface rocks or reservoirs? If so, how much water is still there? Could we use the ancient reservoirs of Mars to support a human colony? And perhaps most significantly, did life arise on the planet during the Noachian period at the same time as life began on Earth? Could that life still be present on Mars today? The most recent explorers of Mars are the Opportunity and Curiosity rovers. Opportunity landed on January 25, 2004, with a planned lifetime of 90 Earth days. In a spectacular testament to engineering excellence, Opportunity remained operational until a planet-wide dust storm covered its solar panels in June 2018. After over 14 years and a journey of 45 kilometers on the surface of Mars, Opportunity was finally declared dead on February 13, 2019. Curiosity is the most massive and most capable spacecraft ever to touch down on a planet beyond Earth. The landing itself was a tour de force of engineering ingenuity and audacity. Engineers described it as 7 minutes of terror, maneuvering a spacecraft from 13,000 miles per hour at the top of the Martian atmosphere to a soft landing on the surface. The mission cost over $2.5 billion and took 8 years to design and build. Delivering almost a ton of fragile rover onto the surface of Mars with pinpoint accuracy is not easy. Mars has a thin atmosphere, so slowing down a spacecraft traveling 10 times faster than a bullet is hard. Yet the atmosphere is thick enough to cause significant heating and uncertainty in the landing site. Previous landers used combinations of heat shields, parachutes, retro rockets, and airbags. But Curiosity was too large and complex for these methods. The engineering team developed a new solution that seemed audacious: the sky crane system. Curiosity encountered the Martian atmosphere 125 kilometers above the surface, traveling at around 20,000 kilometers per hour. The spacecraft flew entirely under computer control with no input from mission control on Earth. This was the first time an autonomous guided entry system was used for an interplanetary mission. A heat shield protected Curiosity from peak temperatures of around 2,000 degrees Celsius. 4 minutes after beginning entry, the supersonic parachute deployed at an altitude of 11 kilometers. The heat shield was then jettisoned at 8 kilometers altitude. With the parachute fully deployed, Curiosity drifted for 80 seconds. At 1.8 kilometers altitude, Curiosity separated from the parachute and dropped in freefall. Then, 300 meters down, retro rockets fired and the powered descent phase began. After the rockets delivered the rover to an altitude of just 20 meters with almost no downward velocity, the audacious final phase kicked in, the sky crane. The rover slowly departed the rocket cradle, attached by 3 nylon wires and an electrical umbilical cord 7.5 meters long. 4 of the rockets angled away from vertical to avoid damaging the rover and continued firing. The whole system approached the surface at walking pace. At 5 meters from the surface, Curiosity unfolded its wheels. At 10:32 p.m., the rover confirmed its wheels were in contact with the Martian surface. It issued one last command through the electrical umbilical: "I'm down, cut the cables and fly away." After a 500 million kilometer journey, Curiosity was delivered safely to Mars, just 2.4 kilometers from its target point. A triumph of engineering ingenuity and brilliance. Curiosity was sent to explore Gale Crater, a 150 kilometer wide impact crater formed during the late Noachian or early Hesperian period. The primary reason for choosing Gale Crater was the unusual central structure, Mount Sharp, which rises over 5 kilometers above the crater floor. There is still debate about exactly how Mount Sharp formed, but the layers visible from orbit along its flanks suggest it is the weathered remains of sedimentary rocks. These rocks once filled the crater and were laid down over time after the impact. Subsequent erosion by the relentless Martian winds removed much of the surrounding rock to reveal the ancient crater floor, while leaving the towering central structure intact. Deep exposed sedimentary layers are extremely interesting to geologists because a cross-section through rock is a cross-section through time. As surface and atmospheric conditions change, different sorts of rock are laid down and chemically modified. As Curiosity ascends the slopes of Mount Sharp, it climbs forward through Martian history. The rock record preserved in those layers holds stories that are billions of years old. Stories about whether, when, and for how long Mars might have been habitable. At the time of writing, Curiosity has travelled almost 19 kilometres from its landing site on the flat plains to the lower slopes of Mount Sharp. It has stopped along the way at each interesting site to study the geological environment. Curiosity's suite of scientific instruments is the most sophisticated ever installed on a spacecraft. The rover is a mobile geological laboratory capable of analysing the Martian surface and the layers just beneath. In early October 2012, Curiosity stopped at a place geologists named Rocknest and scooped up a handful of Mars. The sample of dust, dirt and fine-grained soil was heated to 835 degrees Celsius. The baking process revealed significant amounts of carbon dioxide, oxygen and sulfur compounds. The analysis also suggested the presence of carbonates, which form in the presence of water. Perhaps most surprising of all, the soil from Rocknest didn't just provide indirect evidence for ancient water. Around 3% of the sample's mass was water suspended as small droplets of salty liquid. Curiosity is sitting on the floor of a lost lake, a body of water that filled Gale Crater at the Noachian-Hesperian boundary. The patterns of sedimentary deposits suggest the lake rose and fell in multiple cycles over tens of millions of years. A temporary landscape of ancient streams, deltas and ponds is bounded by the border of the crater. Curiosity has found sulfur, nitrogen, hydrogen, oxygen, phosphorus and carbon, all the necessary building blocks for life. In August 2017, Michael Meyer, NASA's lead scientist for the Mars Exploration Program, summarized the results. A fundamental question for this mission is whether Mars could have supported a habitable environment. From what we know now, the answer is yes. In June 2018, two new discoveries strongly reinforced the idea that Mars was once a habitable world and maybe still is. Curiosity found complex organic molecules a few centimeters below the surface in rocks known as mudstone that form from silt deposited on lake beds. This means all the ingredients for life were present at the time when Gale Crater was filled with water. Detected molecules include benzene, toluene, propane, and butane. Even more intriguingly, Curiosity also observed a strong seasonal variation in methane levels in the Martian atmosphere today. The methane peaked repeatedly in the warm summer months and declined in the cooler winter, which is what would be expected if the methane had a biological origin. This is not definite evidence of life on Mars today. It's thought that geological processes may be able to account for such seasonal variation. Although if this were Earth, a biological explanation would be favoured. Michael Meyer had this cautious response in June 2018. Are there signs of life on Mars? We don't know, but these results tell us we are on the right track. Mars changed from a warm, wet world to a frozen desert during its first 1.5 billion years. Understanding why is complex. A planet's climate is shaped by countless interactions and feedbacks. Mars's atmosphere today is thin and mostly carbon dioxide. We know this atmosphere must have been significantly thicker in the past to support liquid water on the surface. NASA's MAVEN spacecraft arrived in orbit in September 2014 to measure the composition of the Martian atmosphere and understand how it evolved over time. MAVEN operates in a highly elliptical orbit, bringing it as close as 150 kilometers above the surface and out beyond 6,000 kilometers. This path allows it to build a three-dimensional picture of the gases that remain and how their distribution changes. MAVEN's measurements show that Mars is losing atmospheric gases today at a rate of about 2 kilograms per second. The question is, how is the atmosphere being lost and where is it going? The MAVEN team carried out an ingenious analysis based on observations of two different isotopes of the noble gas argon, argon-36 and argon-38. Argon-38 is chemically identical to argon-36, but heavier because it has two additional neutrons inside its nucleus. The ratio of these isotopes is sensitive to the rate at which the atmosphere is being lost to space through a process called sputtering. High-speed electrically charged particles from the solar wind hit atoms in the upper atmosphere and literally knock them out into space. Because argon-36 is lighter than argon-38, it is preferentially lost to space through sputtering. This means the ratio of argon-38 to argon-36 increases over time. Since there's no other way that argon can be removed from the atmosphere, it doesn't react with anything and it doesn't freeze. The argon measurements provide a very clean indication of how the solar wind affects the Martian atmosphere. By using measurements from MAVEN at different altitudes and surface measurements from Curiosity, this elegant experiment enabled the team to determine that 66% of the argon in the Martian atmosphere has been lost over the planet's 4.5 billion year lifetime. Once this rate of argon loss was determined, the rate of loss of other atmospheric components could be calculated. The published results concluded that a large fraction of the Martian atmosphere has been removed to space. Loss to space has been an important process in the evolution of the Martian atmosphere through time. In particular, a large fraction of carbon dioxide, the dominant component of the Martian atmosphere and a powerful greenhouse gas, has been lost to space through interaction with the solar wind. A smaller fraction was locked away in subsurface carbonate deposits, and an even smaller fraction is stored as frozen carbon dioxide in the polar ice caps. These changes appear large enough to account for the change in Martian climate inferred from the planet's geology. Without declining levels of greenhouse gases in the atmosphere to keep in warmth and protect its lakes and oceans, Mars was destined to become a frozen desert world. But why has Earth not suffered the same fate? We are, after all, closer to the Sun and bathed in a more violent solar wind. Why has our atmosphere survived the solar onslaught for several billion years after the Martian atmosphere was stripped away? The answer lies in Earth's magnetic field. When high-energy charged particles from the solar wind reach Earth, most do not smash directly into atoms at the top of our atmosphere because we are protected by our magnetic field. They are deflected harmlessly, stretching and distorting the field out on the night side of the planet. Some particles are accelerated back down the magnetic field lines to Earth's poles, where they collide with atoms and molecules in the upper atmosphere. This excites them and causes them to emit light. This is the aurora, the northern and southern lights. From the International Space Station, the aurora reveals itself as halos dancing around the poles. The colours we see are the result of atomic structure. High-altitude oxygen glows red when an electron shifts into a long-lived excited state. At lower altitudes, a different reconfiguration inside oxygen atoms causes the emission of green photons. Excited nitrogen molecules add a deep red or pink to the lower edges during intense displays. This is quantum mechanics written across the sky, the structure of atoms revealed. The energy to drive the display comes from nuclear fusion reactions inside the Sun. A central component of the web of physical processes that makes the aurora shine is our magnetic field, which deflects the solar wind harmlessly past our planet. Without this shield, the processes that Maven observes, stripping the atmosphere of Mars, would happen on Earth. The magnetic field is one of the most important differences between our worlds. Earth's magnetic field is generated by what is known as a dynamo. The basic physics is simple. Earth's core is composed largely of molten iron, which is an electrically conducting fluid. Plumes of molten liquid rise and cool as they approach the mantle. Earth's rotation swings these columns around into circulating, rising and falling flows. This circulating flow acts as a dynamo and generates a magnetic field. The stability of the dynamo is related to the temperature gradient between the core and the mantle, the radius of the core itself, the rate of rotation of the planet, and numerous other factors. The magnetic field gives every indication of being a delicate phenomenon. It was certainly delicate on Mars. We suspect there was once a Martian dynamo because the Martian crust is still partially magnetized in places, particularly in the ancient southern highlands. This suggests these rocks cooled in the presence of a global magnetic field. The Hellas impact basin, which formed around 4 billion years ago, shows no sign of magnetization, suggesting the dynamo shut down before this impact. Impact basins that formed over 4.05 billion years ago do show signs of magnetization. These observations lead to the current view that Mars had a magnetic field not unlike Earth's, which seems to have switched off just before the Hellas impact. From that point onward, the atmosphere was exposed to the full force of the solar wind. The Maven results tell us this was likely the key driver for the loss of the Martian atmosphere. The sequence of events is reasonably well established, but there is no consensus on how or even if they are causally linked. A complicating factor is the relative instability of the Martian orbit. The planet's obliquity, the tilt of its spin axis, varies by tens of degrees over timescales of a few 100,000 years in response to gravitational interactions with other planets and the Sun. In comparison, Earth's axis drifts gently between 22.1 and 24.5 degrees in a 41,000-year cycle. Even this small change is responsible in part for Earth's periodic ice ages. Imagine what happened to the Martian climate when the polar regions with their reservoirs of carbon dioxide and water ice tilted toward the Sun by 20 or 30 degrees. The stability of Earth's spin axis is maintained by the damping effect of the Moon, which is unusually large relative to our planet. The Earth-Moon system might almost be regarded as a double-planet system. The more we learn about other worlds, the more fortunate our presence on Earth appears. The red planet is simply too small. It lost its heat more quickly than Earth from its smaller core and through its thinner mantle and crust. Geological activity fell markedly after reaching a peak during the Hesperian, and the planet faded. The atmosphere, held more weakly than Earth's because of the planet's lower mass and gravitational pull, and unprotected by a magnetic shield, was stripped away by the solar wind. The surface approached temperatures more in tune with an orbit far from the Sun. Mars's fate was sealed during its formation 4.5 billion years ago. It is too small and too far away from the Sun to have remained a vibrant, active world. Today, faint auroras still dance in the Martian skies, as photographed by the Mars Express spacecraft. Blue ghosts of a Martian past, generated by localized magnetic hotspots scattered across the planet. Despite its 3 billion-year dormancy, Mars had a bright and active adolescence that echoes down the ages and may yet have profound consequences for us, confined for now on her planetary neighbour. There may have been, and may still be, life on Mars. We're looking hard, and the next generation of spacecraft may find evidence within the next decade. The discovery of a second origin of life would have important philosophical, scientific, and cultural consequences. It would mean that given the right conditions, liquid water, active geology, and a sprinkling of organic compounds, we would know that life emerges with a sense of inevitability through the entirely predictable action of the laws of nature. It would be confirmation that we, along with every living thing on our planet today, are an outgrowth of the planet, an extension of geology. We would understand that whatever magic we perceive in the depths of our souls has its origins in the interface between water and heat, and minerals and gas. We are bubbling chemistry that thinks. If it happened on two neighbouring planets in a single solar system, it happened everywhere. We would understand that we are part of a grand living universe. We are not alone. Of even greater importance is the role that Mars must play in our future. Mars is rich in potential. It has reservoirs of frozen or even liquid water below the surface and a great wealth of mineral resources. All the things necessary to support a civilization. Because of its history, this is a world in waiting, a treasure island in stasis. I think in my lifetime there will be Martians. The Martians will be us. We will go to Mars and make it our home, partly because there is nowhere else to go. Mars is the only planet beyond Earth on which we could even contemplate a landing in the near future. I don't mean that we will leave Earth en masse for the new world. This is manifest nonsense. Earth is by far the best planet we know of anywhere in the universe. We were born of it and sculpted precisely and perfectly to flourish on it through the action of evolution by natural selection. Yet it is possible now to build a colony on Mars. I imagine a group of pioneers on the New World living off the land and constructing the infrastructure necessary for tens, hundreds, and ultimately thousands of individuals to follow in their footsteps across the solar system and extend the human frontier for the first time in many centuries. Frontiers are important. The intellectual frontier is the domain of science, and where would we be without the pioneers who felt drawn there? The physical frontier is the domain of adventurers, engineers, and dreamers. And dreamers need somewhere to go. Mars is the step beyond the Antarctic, and perhaps we all need to take it. In our imaginations, our civilization feels untethered to me. We're at loose ends, huddled in a tiny corner of our system. We watch the wandering planets and the wheeling stars and the cycles of day and night and wonder what we're doing. As a consequence, we scrabble around, eking out ever more precious resources on Earth, trying to expand and build more stuff and grow in a thin shell of air on the two-dimensional surface of a small rock. We give little thought to the three-dimensional path marked by the lights in the night. Robert Zubrin, the visionary engineer whose work has inspired many, including Elon Musk, likes to say that ideas have consequences. The worst idea in the history of humanity is that we must compete for limited resources. This is false. The solar system contains raw materials beyond our needs or desires, and they will become resources when we choose to access them. The international tensions created by competition for Earth-bound resources are based on the entirely false and dangerous idea that resources are limited. We have the technology, and perhaps as we drift ever more aimlessly, we may discover the will to unlock the unlimited treasures in the vast solar system of which we are a part. We need to shift our collective consciousness. We burn too bright for this world alone, but that does not mean we should extinguish the flame. We must forge a new path that transcends competition between nations. This requires the wholesale rejection of the mindset that mistakenly compels us to retreat or fight over dwindling resources on a single groaning planet. We must transform ourselves into a multi-planetary, spacefaring civilization. This begins with the colonization of Mars, an achievable goal forged from the human desire to explore and expand without pushing up against someone else's border fence or damaging our planet beyond repair. Imagine the magnificent intellectual and physical vistas, the new technologies, the opportunities, the excitement of creating a new society, the joy of extending our collective experience and hopes and dreams to a new world and worlds beyond. Mars has a pivotal role to play in our future. If we don't go there, we'll never go anywhere. And if we go nowhere, we'll die here. Breathing new life into the old red planet will breathe new life into us. It will be our first step beyond the cradle and onward to the stars. How do we know about events from billions of years ago? The answer lies in rocks. Apollo brought back 382 kilograms of rock from 6 lunar landing sites. As on Earth, rocks can be dated with great accuracy using natural clocks provided by the radioactive decay of certain atoms. The chemical element rubidium, for example, occurs naturally, in a form known as rubidium-87, found in many potassium-rich minerals. It is unstable with a half-life of 48 billion years. This means that over a period of 48 billion years, half of the rubidium-87 atoms present in a rock when it formed will have decayed away, changing into another sort of atom, strontium-87. An older rock will have fewer rubidium-87 atoms and more strontium-87 atoms. There is a clever part to the dating procedure. We don't need to know how many atoms were present when the rock formed. The method relies on the fact that there is another naturally occurring form of strontium that is not produced by radioactive decay. Strontium-86. Strontium-86 is stable and chemically identical to strontium-87. The only difference is that it has one more neutron inside its nucleus. This means any strontium-86 atoms inside a rock today were present when the rock originally formed. By counting the number of rubidium-87, strontium-87, and strontium-86 atoms in samples taken from a rock, it is possible to calculate the absolute time elapsed since the rock formed. On Earth, some of the oldest crustal rocks are found off the southwest coast of Greenland, at a place called Isua. Using rubidium-strontium dating, we know these rocks formed 3.66 billion years ago. The oldest known rock on Earth was found in Western Australia. It formed 4.44 billion years ago. All known samples from Earth's crust are younger than 4 billion years old, because the seething surface of the early Earth meant rocks were constantly being melted and reformed, resetting the radiometric clocks. The same analysis can be carried out on meteorites that have fallen to Earth from space. The majority, over 1,000 known, formed between 4.4 and 4.6 billion years ago, which is consistent with independent estimates for the age of the solar system. The youngest of the moon rocks returned by Apollo astronauts were 3.2 billion years old, and the oldest were 4.5 billion years old. 12 of the samples were over 4.2 billion years old. The variation in age of the moon rocks is extremely interesting and important. It forms the basis of the most accurate technique for dating areas of the moon from which we have no rock samples. We can make a graph showing the age of rocks collected from each Apollo landing site, plotted against the number of craters per square kilometre at the site. Older sites have more craters, which is easy to understand because there's been more time for meteorite impacts to build up. Surfaces created more recently have experienced many fewer subsequent impacts. Imagine there's an area of the moon from which we have no samples, but we do have photographs from space. We count the number of craters per square kilometre. This allows us to estimate when the surface formed. More importantly for our purposes, we can extend this graph from the Moon to Mars. We have to make some estimates of how the number of impacts changes, because Mars is a larger planet with stronger gravitational pull. We also need to account for Mars's different place in the solar system, closer to the asteroid belt, the source of most impacting objects. We can do this with some confidence. This is the primary way we estimate the absolute age of different regions of Mars. The Noachian terrain is oldest and has the highest density of craters, followed by the Hesperian and Amazonian. The northern lowlands have been resurfaced by volcanic activity in the more recent past, which we know because they're relatively free of craters, much like the lunar seas. In this way, the absolute dates we quote for events on Mars are all ultimately tied to the radioactive dating of moon rocks. This is one of the main reasons why the Apollo rock samples are so valuable scientifically. There's another key line on the graph: constant production rate. The number of craters plotted against age would follow this line if the Moon had been subjected to a constant rate of impacts throughout its history. The measurements follow this line until we get to surfaces around 3.8 to 4 billion years old. Then the number of craters increases dramatically. This implies that in the early history of the solar system, there was a time when the rate of impacts was much greater than today. That's not surprising. We might expect the young solar system would have been filled with leftover debris from the formation of planets, and so would be a more violent place. But there is a complication. If we assume the impact rates seen on the oldest lunar terrains were sustained all the way back to the Moon's formation, then the impact rate would have been impossibly high. The amount of mass falling on the surface would have been similar to the mass of the Moon itself. We know that didn't happen, so the assumption is that the rise of the impact rate curve is actually a spike that peaked around 3.9 billion years ago and then returned to much lower impact rates from earlier times. This violent spike in the rate of impacts from space is known as the late heavy bombardment. The cause of the late heavy bombardment is not known, but a leading theory is that Neptune changed its orbit from inside to outside that of Uranus. The resulting gravitational disturbance deflected a storm of icy objects in the distant Kuiper Belt toward the planets of the inner solar system. We might reflect on the interconnected nature of knowledge and of the solar system. Exploration of the Moon provided us with the intellectual tools to date the surface of Mars using scars delivered by objects deflected into the inner solar system by events that occurred far away in space and time, beyond the orbit of either world. The story began before the solar system even truly existed. 5 billion years ago, a vast interstellar cloud of dust and gas, at least 65 light-years across, began to collapse under its own enormous weight. It fragmented into a collection of smaller, denser cores. One of these gigantic clumps formed what is known as the pre-solar nebula, the embryo from which every part of our solar system would develop. In this dense cloud of gas, comprised almost entirely of hydrogen and helium, hung every atom that would go on to form the Sun, the planets, and every element that would define the character of each of these worlds. This included the ingredients of life, the components of you and me. What triggered this cloud beyond the tipping point and onto the next stage of its evolution is lost in the eons of time. But astonishingly, we have been able to pull together scraps of evidence to guide us. By studying some of the oldest meteorites ever discovered on the surface of Earth, we've been able to get a glimpse of the time when it all began. Locked away inside these ancient meteorites are unmistakable signatures of rare forms of iron that we believe can only have been created under very specific conditions. The only place in the universe where these rare isotopes can be formed is at the heart of giant, short-lived stars at the very moment they explode. In other words, they are the product of supernovae. This clear chemical fingerprint from rocks dating back to the earliest days of the solar system, over 4.5 billion years ago, suggests our solar system emerged among a cluster of thousands of stars in a large stellar nursery. Perhaps it was not unlike the Orion Nebula, the star-forming region that lies closest to Earth at 1,500 light-years away. You can even spot it with the naked eye in the night sky. From that collapsing cloud came the Sun, the planets, and every atom that makes up our world, including the ingredients of life. We are quite literally made of stardust, forged in the hearts of ancient stars that exploded long before our solar system existed. The exploration of Neptune, Mars, and the other planets teaches us profound lessons. The solar system is not static. Planets change, atmospheres are lost, climates shift dramatically over time. Neptune's winds howl at supersonic speeds, powered by mysterious internal heat. Triton shoots ice geysers into space, a captured wanderer from the distant Kuiper Belt. Mars transformed from a warm, wet world to a frozen desert in just 1.5 billion years. Only Earth has maintained the delicate stability over 4 billion years that allowed life to flourish and evolve into the rich ecosystem we see today. But this stability may not last forever. Understanding why Mars and Venus diverged so dramatically from Earth helps us appreciate the fragility of worlds. It warns us about our own future and the care we must take with our precious planet. Yet Mars also beckons as humanity's next frontier. This is not just about exploration for its own sake. It's about ensuring our survival as a species and expanding our horizons beyond a single world. The colonization of Mars represents an achievable goal that will transform us into a multi-planetary civilization. By becoming a spacefaring species, we take our first true steps beyond our homeworld and toward the stars. We reject the false and limiting idea that we must compete for scarce resources. Instead, we embrace the reality that the solar system contains unlimited potential for growth and development. Mars sits there waiting, rich in water ice and mineral resources, ready to support human life. The pioneers who go there will build the infrastructure for thousands to follow. They will create a new society, develop new technologies, and open up magnificent vistas, both intellectual and physical. Going to Mars will breathe new life into humanity. It will remind us that we are explorers and dreamers, not meant to be confined to a single world. It represents our first step beyond the cradle of Earth, the beginning of humanity's journey to the stars. The journey continues, and the greatest adventures still lie ahead. From the depths of the Kuiper Belt to the frozen plains of Mars, from the windswept clouds of Neptune to the volcanic landscape of Triton, our solar system is filled with wonders waiting to be discovered. Each world tells part of the story of how we came to be here. We are children of the cosmos, made from the ashes of ancient stars, living on a fortunate planet that has maintained stability long enough for life to emerge and evolve. Now we stand ready to take the next step, to become a truly spacefaring civilization, and to write the next chapter in humanity's story among the stars.